Okay, welcome to problem solving session for linear algebra. I'm Siddhi Balu Ambore from IIT Gandhinagar, and we will discuss the problems related to the syllabus from week 2, that is the problems related to linear independence, uh, dimension basis, and a few problems related to uh, replacement theorem. And so let us start. We'll start with the first problem, and it is related to, we will check that whether the given set is linearly independent over a vector space or not. So let's start with our question 1. So question 1 is check whether which of the following are linearly independent sets. Okay, so we'll start the first one, and it contains these elements. In R4. Okay, so these are all vector spaces over R, and we are working and we will be checking that whether this vectors this set is linearly independent or not over R in R4. So any guess? So you know what is linearly independent, right? Something which is not linearly dependent. So when we say that something is not linearly dependent, it means that if I am to write a linear combination of these elements over R, then all the coefficients or scalar multiples of these vectors must be 0. That is called linear independence of set. Okay, so let us check and how to do it. That let A, B, C, D belongs to R, then we write it as linear combination like A 0 0 minus 1 plus B 0 1 0 minus 1 plus C 0 0 minus 1 1 plus D 0 comma 0 comma 0 comma 1, and this we would be checking whether, and we want to find what this A, B, C and D are. So if all of them are 0, then we will say that this is linearly independent set, and if it is not, then this will be linearly dependent set. Okay, so what does this mean? So I will be multiplying this scalar multiples inside to these vectors, and I will write them directly. Then it will be A plus B. No, B won't be there. A plus first coordinate is only A. Okay, A, then B, then minus C, then minus A, minus B, minus or plus C. Oh, this one is like this, 1 comma minus C. Then it will be C minus A minus B minus C plus D. Okay, and this equal to 0 0 0 and 0. So what this will give me? It is linearly independent. Okay, and we will check that right now. So what is we are getting when we compare them component wise, then it will be A is equal to 0, B is equal to 0, C is equal to 0, and this last component minus A minus B minus C plus D is equal to 0, and since A, B, C are 0, we will get that D is also equal to 0. So if at all, if we have any linear combination of these four vectors giving us 0, then ABCDs must be 0. Then this implies that this set, let us call this set to be A. The A is linearly independent set in R4. Okay, any doubt? anyone has doubt, what is the definition of linear independence or dependence? If that is, if anyone has doubt in that, please ask. I will explain that once again. And I hope this is clear. So shall I move further, or you people need any more explanation, or is it okay? It's clear, right? Okay, so we will go to second similar kind of question, and we consider this set B, and these are the elements: 1, -3, -2, 4, 3, 4, -4, 5, and -2, 6, 4, -8 in M2R. Okay, so to make our life simple, let me name these vectors. Let us call this vector U, this as V 3 -4 4 5, and this as W -2 6 4 -8. And what is your guess? Whether this is linearly independent or dependent? Can somebody tell me which two of these vectors, of these three vectors, are linearly dependent? U and W. Okay, as Karthikeyan said, U and W. Hetvi also said U and W. So we can clearly see that here U is equal to, or I would say W is equal to -2U, right? So if I to, so we have this, right? Then we can simply write it as, so this gives us what? 2U plus W is 0. Okay, and I can simply write that 2U plus 0V plus W is equal to 0, and this W means 1 into W. So we can have this A is equal to 2, B is equal to 0, and C is equal to 0, C is equal to 1. In this case, AU plus BV plus CW is 0, and when I'm writing this 0 is my matrix 0 0 0, right? Okay, do not forget that this 0 is not the normal 0 in real. Okay, so 0 0 0 0. And we have a set of scalars, or scalars such that one of them, at least one of them is non-zero, and but the linear combination is giving me the 0 of the vector space. So these imply what? This set U V W, that is our B, is not linearly independent, or it is linearly dependent. Okay, any doubt here? If you want, you can clearly go and write like what we did here, that A into U plus B into V plus C into W, and write equal to 0, and we will get 4 equations in 3 variables, and you can solve those and check whether you are getting whether ABCD you are getting all of them are 0 or not. Okay, you can also do that, but from this set we can clearly see that W is -2U, so that's why we directly go. I mean, when we say that something is linearly dependent, we need to have at least one linear combination such that the scalars are non-zero. At least one scalar must be non-zero, and if we can have such pairs where it is non-zero, then set becomes linearly dependent. We need not check all possible linear combination. If we have one, that is enough to say that set is linearly dependent. Okay, I hope that is understandable. But when we have to check for linear independence, in that case we have to show that, give me any ABCD, you need to show that those scalars are 0, then only we can say that they are linearly independent. there is a difference between showing something something linearly independent and something linearly dependent. If you have any doubt, please write in the chat. I will clarify it. Okay. So move to the third question, third from the same question. Consider now this set. Let us call this C. Okay, no, but x cube plus 2x square minus x square plus 3x plus 1 and x cube minus x square plus 2x minus 1 in this P3R. P3R means polynomials of degree less than or equal to 3. Okay. Okay, and these are polynomials in X over coefficients with coefficients from R. Okay. I hope P3R, you know the definition of P3R. So we want to check whether this C is linearly independent or not, or whether it is dependent. So we will again start with the linear combination. So let us write A into x square plus x cube plus 2x square plus b into this set minus x, this element minus x plus 3x plus 1 plus c x cube minus x square plus 2x minus 1 and is equal to 0. So this 0 is 0 from our P3R, that is normal 0 in our real numbers R. So what does this imply? So I will accumulate all the coefficients of the x cube, x square, x and 1. Okay. So what we will get? A, here we do not have anything. In second term, we do not have anything of degree 3. In third, I get C. Okay, so A plus C, x cube plus second one, for this, I have 2A from the first element. From second element, I have this minus B. Third one, I have minus C into x square plus, again, now first one does not have any coefficient for x. Second one has 3B and third one has 2C x, and last one is for the constants, I have b minus c is equal to 0. Okay, so from this what I get? A plus c is equal to 0, 2a minus b minus c is equal to 0, 3b minus 2c is equal to plus 2c is equal to 0, and here b minus c is equal to 0. And once I have b minus c is equal to 0, what does this imply? B is equal to c. Okay. And I have this. Okay. Let me call this 1, 2, 3. Okay. I have b is equal to c. Then if I substitute that in second, then second becomes 2a minus b minus c is equal to 0. Then I will substitute b to be c. Then I guess 2a is equal to, this implies 2a is equal to 2c. This implies a is equal to c. And from first, what I get? A minus c, a is equal to minus c. So a is equal to c and a is equal to minus c. What does this imply? A is 0, right? Both are 0. So we get a is equal to c is equal to 0. And from the third equation, we again get that b is equal to 0. Any doubt? Or if this is confusing, we can substitute. Or let me keep this. B is equal to c in this, and I get 5. C is equal to 0. This will give me c is equal to 0. and then substitute C is equal to 0 and B is equal to 0, and from second equation itself I will get A is equal to 0. I mean, there are many ways you can do this, but ultimately you will get that A, B, and C, all of three are 0. A is equal to B is equal to C is equal to 0. And therefore, our this set C is linearly independent. In doubt here? How we are like taking all the coefficients of degrees together and then comparing. So we are what exactly doing is, we have on the right side x cube plus 0x square plus 0x plus 0, okay? And then we are comparing this as coefficient wise or component wise comparison. And then we are getting these four equations, and then we got that ABC needs to be 0 if we have such kind of setup. Okay, so if you have doubt, please write it in the chat. Otherwise, I will move to further question. And this pi comma 0 e comma pi, let me call this set 0 d and 0 comma e in R2. Can somebody tell me whether this set is linearly independent or dependent, or what it is? You can unmute yourself and also speak. That's not a problem. So Hetvi is suggesting that this is sorry,
dependent.
Dependent, right? This is dependent. Okay, so quick thing to say that this is dependent is okay, we are in R2, and over R we know the dimension of R2 is 2. Okay, and here we have this 3 element set, and from the consequence of replacement theorem, I would say that once we have any set which has cardinality greater than the cardinality of basis, then it is linearly dependent set. That is the theorem. Just a second. Yes, replacement theorem. One of the corollary from replacement theorem. But if you are not very clear with that, let me for to be clear with this, solve this, and we will see that why this is. I mean, just because we are seeing this e pi and everything, we might think that okay, this would be linearly dependent set, but that's not the case. Okay, so let me write this a pi plus be comma b pi plus ce is equal to 0 comma 0. And what does this give me? A pi plus be is equal to 0. Component wise I am comparing, and b pi plus ce is equal to 0. And from this I get a is equal to e by pi minus e by pi b, and this is not the right way to, or it's okay. It's okay. And from here I get c is equal to minus e by pi b, no, minus, this is be, b pi ce, b pi ce. C is equal to E by pi. Is it correct, or am I making some mistake here? Can somebody tell me? B pi plus CE. So I get C is equal to B pi I by E. Okay. C is equal to B pi by E. And if we take this B to be 1, then I can have this linear combination. A is minus e by pi into pi plus b. B is 1e, comma, again this 1 pi into plus minus pi by e, b, e, and this will be 0 and 0. Any doubt? So in short, if I choose b anything in R, then A to be minus e by pi b and C to be minus pi by EB. This will give me infinitely many non-zero coefficients for A, B, C, and this will give me zero, that this set is not linearly independent. This set D is not linearly independent. Okay, any doubt here? Hedvi, is it clear, like why this is not a linearly independent set? Okay, you can directly solve, and also the one of the corollaries which is proved in the lecture from the replacement theorem also clear that this is not a linearly independent set. Okay. So if you have any question in the exam of this sort where it is asked whether to check linearly independence or not, the first thing to do is, if the vector space is such that you know its dimension, or you know its cardinality of its basis, then just check what is the cardinality of given set. If it is greater than the dimension of the vector space, then clearly it will be linearly dependent set, like what is happening in the this fourth example. But otherwise, you have to check like this. For example, in P3, you have to check since the cardinality is less than, it could be linearly dependent or independent set. Okay, so please check it carefully and do the problems accordingly. Okay.
If
Now,
it is R3, how to solve? We have to solve and then find out. R3.
which ones? Which one, sir?
If it is R3, if it is
Yes,
R3,
sir.
how to?
In R3, you are asking me.
Yeah, yeah.
In
And if
R3,
it is R1, what is the directly can we infer anything?
in R, okay, so if I have R, then R is one-dimensional vector
Yeah,
space
yeah.
already.
So it is dependent. That is clear. If it is
Yeah.
R3 means?
R3 means it will have these kind of components, right, sir? A, B, C.
Yeah, yeah.
Such.
So we have to solve and find,
Yes,
correct? No?
sir. Definitely, sir. Yes. So what we have to do? So if it was R3 having 4 elements, in that case, we have to kind of go and check. We need not, I mean, let me just write this in statement. If V has dimension D, or dimension of V is D, and if any set A has cardinality to be some K which is greater than D, then A is linearly dependent. Okay. So in that case, if I am my V is R3, and any set A with cardinality greater than 3, that is 4, 5, 6 onwards, then we can directly say that it is linearly dependent. However, if cardinality of A is less than or equal to 3, I mean, if it has 2, or I mean, one element is always, if any element, singleton set having non-zero element is always linearly independent. Okay, for 2 and 3 on 2 and 3 in this particular set, we have to check whether the set is linearly dependent or independent or not with using this linear combination method. I hope that is clear. If you have any doubt, you can unmute and ask or write in the chat. And if not, then I will move
This
to.
is week 1 or week 2?
This is week 2, sir.
Week 2.
Yeah. So let us move to this second question, and we check whether the following statements are true or false. Okay. So first let me write that every vector space over R has finite basis. And what is your guess for this? Can anyone would like to guess whether it is true or false?
True.
Uh, it's okay. So Karthi said is true and Karthikeyan said it's false. Okay, so every vector space, it is saying that give me any vector space, I can say that it has finite basis. I mean, it is finitely generated over R. Since Karthikeyan said it's false, can you give me any counter example where this does not hold? Or those who said true, the answer is false. Can you all think of uh, a vector space over R which has infinite basis or cardinality of basis is infinite? Okay, if not, so R3 can have infinitely many linearly independent vectors. It's not asking that. And that is completely different thing. But what we have is, they are saying that give me any vector
Number is
space.
a basis, right? Any real number will form a basis, right? In R.
No, it is not saying that a finite basis. It is saying that every vector space, that V is a vector space over R. Then what I am asking is whether dimension of V is always finite. Dimension of V is always finite or not. Or it is asking that it has finite basis, means the cardinality of basis is finite.
No, no, no.
Exactly. It's not the case, right? Because
Yes.
see, we can have this vector space of set of all polynomials over R in variable X. And here we know that basis of this vector space, or let me clarify which, over R is this set 1, x, x square, x cube, and so on. It continues. It has infinitely many elements. So basis of this vector space, if we take V to be this set, a set of all polynomials over R, then this is a vector space over R which does not have finite basis. The basis of this set is infinite. Any doubt? So this is not true. Okay, or let me write, this is false, that the basis we can have infinite basis, a vector space with the infinite basis over R. Any doubt? Aarti, is it clear why this is false? Yes, okay. So let's go to second question. Every finite dimensional vector space. So now our vector space has finite dimension. I mean, the cardinality of a basis is finite over R, contains infinitely many distinct linearly independent vectors. And when I say this, I'm not saying they are linearly independent, I mean distinctly. I mean, I'm not saying that take this set A in that vector space, and now we have infinitely many independent vectors. No, I'm saying that if I have a subset, let me write V, a vector space, I am simplifying the statement over R. And what I'm saying, suppose dimension of V is n, okay, some finite number. What I'm saying is that can I have a set S with the containing infinite elements? And S is linearly independent. I mean, is it true or false? What is the guess? I mean, vector space is given, it has n dimension. Now I'm saying that S is a finite dimensional vector space, a subset or in a finite dimensional vector space, and its cardinality is infinite. And I'm asking whether this set S is linearly independent or dependent. Can somebody tell me why this is not true?
If the cardinality is more than the dimension, then it will become dependent, right?
Yes, exactly. That will happen. Okay, so since S is infinite, S has infinite elements, we can choose any, for example, here the dimension is n, we can take this S1, or let me write n A1 to a n plus 1 elements in S. And since this set has cardinality, or let this set A has cardinality equal to n plus 1, by what I wrote here earlier, that if dimension is greater than or the cardinality of set is greater than the dimension, the set becomes linearly dependent. And using that, we can say that A is not linearly independent, then its superset cannot be linearly independent. Okay, so S need not be, S is not in fact linearly independent. Okay, so what we have to learn from this statement is that in a finite dimensional vector space, any infinite a set with infinite cardinality can never be linearly independent. Okay, so is it clear? Anyone has any doubt? Please write in the chat if you are facing any difficulty. Okay, there's no comment. I assume that it is clear. And all these statements which I'm using, that cardinality greater than the dimension, and that's why the set is independent or dependent, all these statements are proved in the lecture, and you can go through even the notes, and it is written very nicely that how these statements are true, and they are also proved nicely. Okay, so I will move to this next question. If you face any doubt, please write it in the chat, that every, and so therefore this statement is false. Okay, that every finite dimensional vector space over R contains infinitely many distinct linearly independent elements. This statement is false. And now we move to next question, that every subspace of finite dimensional vector space over R is finite dimensional. And what is your guess here? Any guesses? In short, what I'm saying that V is a vector space, or let me have a vector space over R, and W is V is subspace. Then what I'm asking is, what is dimension of W? It is true. Okay, as HV said, it is true. Because of the theorem which is proved in the lecture, and it states that if V is finite dimensional vector space, and W is subspace of V, then dimension of W is less than equal to dimension of V. And in fact, if dimension of W is equal to dimension of V, in that case, W becomes V. Okay. So this is the theorem. This is the last theorem proved in the lectures. So you can also go through the proof of it. And from this theorem, we can directly say that any subspace of a finite vector space has finite dimension. But this is not the case when our vector space V is infinite dimensional. Okay. So we can have a vector space which is infinite dimensional, but its vector subspace could have both infinite or finite dimension. Okay, so can somebody give me example of this? That vector space is infinite dimensional, but its subspace, two subspaces of it, one with infinite dimension, one with finite dimension. Any guess? Or I will give you a few seconds. If not, then please write it in the chat. Or we also
False, right?
discussed.
False, right?
Sorry, sir.
It is false, right?
Yeah.
If the vector,
Yes, sir.
it's if the vector space is of infinite dimension, and in the subspace, if we have one with infinite dimension, one with finite dimension, then it will again become false, right?
I mean, we can have both of them actually. From the so what this statement is, if our vector space to start with, if it is finite dimension, then all its subspaces will be finite dimension. But in case of infinite dimensional vector space, its subspace could be finite dimension, could be infinite dimension. For example, if I take this again, this PR, the set of all polynomials, and it has basis this, right? I mean, we wrote 1x x square and so on. Then we can take this W1, which is generated by these elements, x square or beta of W1, x cube. I mean, with this is polynomials with coefficients or with constant equal to 0. And we can take this beta to be W2, 1x x square. This is P2R polynomials with degree less than or equal to 2. So in case of infinite dimension case, so in case of infinite dimensional vector space, its subspaces could have finite dimension or could have infinite dimension. Okay, so we do not have concrete statement in case of infinite dimensional case like this that every subspace will be finite dimensional. Is it clear?
Yes.
Okay. Next, this is okay. There exists a vector space over R such that the collection of all bases of V is finite. I mean, it is saying that if can we have a vector space over R such that we can have only finite set of bases. I mean, I'm not asking that vector space is finite dimension. I'm asking that it has only finitely many vectors basis element or basis set. I mean, what I'm asking is that there exists a vector space V over R such that beta 1, beta n, where each beta I is a basis of V, are all the basis of V. Is it true? I mean, it says that my vector space has only finitely many bases. The number of bases, for example, I'm explaining you what this question is asking, that this is R2, okay? We will start with this R2. This is vector space, this is basis, this is beta 1, let's say. This is one basis of R2. This is also one basis of R2. Or I can just take, this is a basis of R2. They are saying there are only finitely many such pairs possible.
No.
Right, it's not true. Even Hetvi said it's not true. Karthikeyan also said it's not true. So this statement is false, as you say, as you all guessed correctly. And why this is, I mean, you do not need to list out all the vector space, all the bases like this. Suppose V is any vector space, okay? And suppose this beta is its basis. How to write? Let's say beta 1, no, B1, B2, Bn, and so on. It could be finite dimension, infinite dimension, I don't care. Okay, but if this is the basis, I can always modify this, right? Beta prime to be alpha B1, alpha B2, alpha Bn, alpha Bn plus 1, and so on. And this is new kind of basis of vector space V again. And note that this will again span our vector space V, and this will also have the same cardinality if we are in finite dimensional case, and so on. And in this case, they were asking about finite dimensional vector space. So let us take this to be finite only. Okay, this, when I vary alphas, alpha non-zero, this will always give me a new vector space for my vector space V, a new basis for my vector space V. Any doubt here, like how we can generate infinitely many bases from the given basis? And you can check clearly that this will be linearly independent set, because if this has some, I would say, if this beta alpha has some linear combinations like this, such that this is 0, then I always multiply this by 1 by alpha, and I get my original basis beta. And again this a1, b1, a2, b2, and an, bn becomes 0, and this again gives me that a1 is equal to a2 is equal to an is equal to 0. So this set will always keep on remaining linearly independent. Is there any doubt like how this is happening, or how we are having this infinitely many bases or infinitely many different bases for our vector space V. Okay, so I hope it is clear. Any doubt, please write, or if it is clear, please mention that it's clear to all of you. Oh, okay, it's clear. Okay. So let's move to next question. In the similar, so this statement is false. Okay. Uh, this is not true because we could obtain infinitely many bases from for the given vector space. Let's move to this question, that every subspace of an infinite dimensional space over R is finite dimensional. And we just discussed this, right? What was the answer to this? We discussed this a few minutes back. Can somebody tell me what this is, whether it's true or false, or your guesses? They are saying that if I have an infinite dimensional vector space over R, every vector subspace is finite dimensional. As Karthikeyan and Hetvi said again, it is false. Okay, so this is false. And to be precise, let us give a counter example which we have been seeing so far. We can take this again, PR with basis 1, x, x square, and so on. And we can take W again generated by constant term is equal to 0 in V, and it is generated by x square, x power n, and so on. So this is again, yes, again, it could be infinite, it could be finite. But our question asks that it is for every, so that is false. Okay. So it is any doubts? So, as we saw in the previous example, so what I could see is when we are given such statements, make sure that you are able to understand the statement first. Okay, that what the statement is asking, and properly define it mathematically, and then go on solving for it. Okay. So this need not be true, and we can have finite or infinite dimensional vector subspaces for the infinite dimensional vector spaces. Any doubt here? And here, no, right? If not, then we will move to this next question. And here we have this setup for this question, that let V be a vector space. Okay. And let A be any subset. So let me write here subset. Do not confuse this with vector space, vector subspace. Subset, and we denote by this mod A the number of elements of A. Okay. So let L be a non-empty linearly independent set or subset of a vector space V. Okay, so L is any linearly independent set. And this T be a, and this T be a linearly dependent set of V, and but T need not necessarily span V. Okay, I mean T is linearly dependent set, but T is not. T could be or T could not be the spanning set of V. Okay, necessarily. Okay. And they are asking this first thing, that can we have that mod T or the cardinality of T cannot be greater than cardinality of L. Can somebody guess what this will be? When
If
we
it
have
is
to check.
not in the span, then it can be different.
Yes, sir. So, check whether true or false. So, what is the guess? It could be false, right? So can you give me explicit example? A vector space, a set T and set L, such that cardinality of T. So it is false. So we want T and L such that cardinality of T is greater than cardinality of L.
R3 is not in
Yes.
R2.
Yeah. So we can take V from R3, and T is linearly dependent. Okay, so we can just take any. Let me take 0, 1, 0, 0, 2, 0, 0, 3, 0, and 0, 4, 0. Okay, and I mean we can just keep on increasing. We just want it to be linearly dependent set, and as they have said that it need not necessarily span, so we don't care. And we can have this L to be set. Can somebody guess what we can take L to be?
R1, R2 means,
Yes, the standard basis of R3.
yeah.
Yeah, so we can take this one. Yeah, and now we very well have this cardinality of T is 4, which is anyway greater than cardinality of L, which is 3. Okay, so the cardinality of T and L, I mean T cannot be always have, uh, I mean they are saying that T cannot have greater than cardinality greater than L. So this statement is false, okay? Because we just have the vector space and set this T and L such that cardinality of T is strictly greater than cardinality of L. Any doubts here? And we can have, yes, and Hitvi had also suggested that we can take standard basis of R3, yes. So, so this is clear, right? So we can, and this is not very special example. We can have this in many different cases, and try to generate such examples to get hold of solving questions in the exam or for the assignments as well. So let me take this. Let me write on the new page that now they are asking that cardinality of L cannot be greater than cardinality of T. And what is the guess? Cardinality of L cannot be greater than cardinality of T. Now L is linearly independent, okay? And T is linearly dependent. And now they are saying what? The linearly independent set cannot have cardinality greater than linearly dependent set. And what is the guess here? Since no response. Okay. Hetvi is saying this is true. I mean, is it always true that linearly independent set cannot have cardinality greater than linearly dependent set? I mean, this is false, okay? Because let us see this example. I can take V to be R3. Yes, Aarti said it's not true. Because, see, we can take L to be again standard basis. Oh, let me write this. 1 0 0 0 1 0 and 0 0 0. Oh, sorry, 0 0 1. This is linearly independent set. And let us take T having only these two elements 0 0 0 and 2 0 0. And here clearly the cardinality, this is linearly independent, this is linearly dependent, and cardinality of L is greater than cardinality of T. Is there any doubt? Hetvi, is it clear like why this statement is false?
The question itself, sometimes while reading, and we are not able to understand.
Yes, sir. That happens. That's why understanding it and writing it mathematically really helps. So, and read the question carefully, like what it is asking. It is not saying it is as, and this hint here given that T need not necessarily span V is really important. Okay. So we are taking any random two elements which are linearly dependent, and that's why this is happening. And you can think like if I put that condition on T, that it has to be necessarily span our vector space V, then which of these statements are true and which of these are false, and so on. Okay, think like that so that you will get used to answering such question and it will help you in the exam also. And not final, but yeah, next question, that L cannot be equal to cardinality of T. Cardinality of L cannot be equal to cardinality of T. The
False.
cardinal. Okay. Again, it is false. And again, I am taking L to be same. We can have this basis. Doesn't matter the order. And T, I can take this 0 0 or 2 0 0 and 0 0 1. This is linearly dependent set. This is linearly independent. And however, the cardinality of L is equal to cardinality of T. Okay, is it clear now to everyone? That the cardinality of linearly independent and linearly dependent set is can have any inequality, like it could be greater than, it could be less than, and it could very well be equal to each other. Okay, but this condition that T, the linear dependent set which we are choosing here, it is not necessarily spanning our vector space V. Okay, please go and think that what will happen if that condition is imposed on the set T. Okay, like if we choose T to have a condition that T must span the vector space V and T is linearly dependent, then what are all the things which could happen, and so on. Okay, and which of these statements might become true and false, and so on. Okay, so please think about it, and if you have any doubts, please write it in the discussion forum. And fourth, like any subset of L is linearly independent. Okay, now they are not comparing this L with the T. They are just saying that L is linearly independent set, and they are asking whether any subset of linearly independent set is linearly independent or not. So what is your guess? It's true. So Karthikeyan said that it's true. Okay, so it's true. So we need to prove this statement. Yes, Aarti also said that it's true. So this is a true statement. And now what we need to do is we need to kind of prove this statement because this is a general statement. Vector space is given to us. L is any linearly independent set, and they are saying that any subset of L is linearly independent. So what can we do here? So let us start with L dash, which is a subset of L. And let us try to prove this. And we have to show that L dash is linearly independent. Okay. So let us start by contradiction. So suppose that L dash is linearly dependent set. Okay. Then what this will happen that then there exists A1 to AN in L and scalars. Or let me write V1 to Vn in L dash and scalars A1 to AN in R such that A1 V1 AN Vn is 0 and not all AIs are 0. Okay. But then what we have this V1 to Vn which we have here are belong to L dash, but this is also contained in L. So what this gives me that this linear combination is true in L also. And then what I will have that this V1 to Vn, which are part of L, are linearly dependent set. But what is given that L is linearly independent set. So this contradicts the linear independence of L as V1 to Vn belongs to L, which has linear combination giving with non-zero coefficients giving 0. I hope this is clear. Any doubt like how this is happening? Is it clear? Like any subset of a linearly independent set will always be linearly independent. Because if the smaller set becomes linearly dependent, we can have this non-zero linear combination and that will hold again in our bigger set which is linearly independent and which will contradict the linear independence of the bigger set. So any subset of a linearly independent set is always a linearly independent set. Okay. If you have any doubt, please feel free. Okay, so Karthik and Aarti said that it's clear to them. Okay, so if not clear, then please ask in the chat. And yes. And last, and this one is related to T. So any subset of T is linearly dependent. Now it's other way around. Okay, so what we had asked earlier was that whether the subset of linearly independent set linearly independent. Now they are asking whether any subset of linearly dependent set is linearly dependent or not. So what is the guess? This one is true. Yeah, I wrote. So any guess like what? Okay, it's false. Not necessary. False. Yeah. So all the guesses are false, not necessary, and false. So it's correct. The any subset of linearly dependent set need not be linearly dependent. Okay, and again, what we were working so far, we can take this set 1 0 0 0 1 0 and can take 2 0 0. Okay, so and as Hetvi said, it need not be linearly dependent. It could be, but it need not be. For example, if I take this subset of T dash 1 0 0 0 1 0, then this is linearly independent. Or let me and this T double dash, if I take this elements and this one, this is linearly dependent. Okay, so it depends on what elements we are choosing. We can have linearly independent and linearly dependent both subsets for a given linearly dependent set. Any doubt? Okay, no doubts. If any doubts, please feel free to ask and write it in the chat. Okay, so these questions were related to the cardinality and subsets of linearly dependent and independent set. And please, this condition was really important to get the counter examples, but I would suggest that please impose this condition on the T, that take T to be linearly dependent subset of V which spans V, and try to solve all these 5 questions and check how you get the answer and so on, which remains like if the true statement remains true in that case, whether the false statement remains false in that case or not. Okay, it will be good exercise. Okay, we'll move to next question, question 4, and again we have to check whether the statements are true or false. Okay, so the dimension of the vector space of all n cross n matrices is n square. Okay, for R. So it is saying that, so you know set of all matrices. So it is set of all matrices. So it is MNR. It is generated by all such elements. So that is Aij belongs to R and this. So they are asking about the dimension of this vector space. So this is our vector space V, and they are saying that dimension of MNR is n square. So they are asking whether it's true or not. Or what is the guess? Okay. Why the dimension of vector space of all n cross n matrices? So if it is false, then what is your guess, Krishna? That what will be the dimension then? We have a matrix of one dimension. Okay. Why this statement is false, I do not understand. They are saying that dimension of MNR of the vector space of all n cross n matrices is, dimension of MNR is false. N square. Why is this false? So let us choose n to be 2. Then what this is this vector space. A, B, C, D, or A11, A12, A22, A21, A22, such that A11, A22, A21, A12 belongs to R. And what is dimension of this vector space? You know what is dimension, right? It is cardinality of the basis. What is the basis of this Mn2R, M2R? What is basis of M2R? Can somebody give me? You understand what basis is, right? It is a spanning set. Yes, Aarti said it has, I mean, the basis has cardinality, I mean, dimension of M2R, that's what she's saying, is 4 in this case. Okay, and elements are this, like A11 we can take, and this plus A12, 0, 1, 0, 0, plus A21, 0, 0, 1, 0, comma, A22, let me write this here, A22 plus 0, 0, 0, 1, such that A11, A22, A12, A21 belongs to R. This forms basis, right? And this can be done for any higher dimensions as well. I mean, if I have this for n dimension, then I can always do this in case, I mean,
Then it is n squared. Then it
yes,
is n.
it is n square because
Hmm.
it has n square many elements here. I mean, each component I can choose A11 and then this 0 all the way up to 0, 0 all the way 0 and everything 0 here. Okay. Similarly, for A12, I can do this. A first row, second position. I mean, this will be 0. This one, now again, everything is 0, 0, 0, 0. Here 0, 0, and so on. Not here, comma, plus. And I keep on continuing. It's all in case of symmetry. That's what I'm asking. This is just when I'm saying it's not talking about the vector subspaces. It is saying the dimension of all the vector space, a vector space of all n cross n matrices. So our vector space V, it is asking about V, which is M2R. Okay. And we have to ask, they are asking dimension of M2R. Those are all vector subspaces of M2R. That is what we will do in next few minutes. But for this question, for this particular, they were just asking for all the elements of MNR. How can we generate all possible elements of MNR and what will be the basis in that case? So here it will be n square because there are n. We can choose this n square many elements here. And similar to what we did in M2R case, this will always, I mean, we continue this and last element will be this ANN 0, 0, 0 and last here everything is 0. Okay, and such that this Aij belongs to R and 1 less than equal to Ij less than equal to N. Okay. So this has dimension because what is this? What is size of this matrix? This is A11, A1n, A21, AN1, A2n, ANN. And this has n element, this has n elements. I mean, each row has n components. So nn, and these are n many rows. So this is n times n. So which is n square. So that's why dimension of MNR is n square. Okay, choose n here and the dimension will vary.
So the thing is that even for rectangular matrix also row only will govern, correct, right?
Sorry, sir.
For rectangular matrix also row only will govern.
No. In rectangular matrix, it will be whatever the order. So in case of if I take m n cross m matrices, then it will have now, for example, it has n rows, right? So
Yeah.
A1n up to an, sorry, not 1 and here I have m columns. So A1m, ANM. So now what I have here, m many elements, here m many elements, here m many elements, and how many rows? N rows. So it is m into n many choices we have. So dimension of these rectangular matrices, here it will be n into m.
Okay.
Okay. Mn in case of rectangular matrices, exactly, has we suggested? Yes, it will be n into m. Is it clear now? So all the possibilities of components we have similar will be the dimension in this case. So in general case, in in square matrices of order n, it will be n square, and for rectangular matrices, it will be n into m or m into n, however you choose the number of rows and columns. Any doubt here? Other? In case of rectangular matrix, any confusion? No. Okay, so Aarti and Karthikeyan said no doubts. So let us go to this second one. And now what Hetvi suggested will come into picture. So now we have this, this second question where they are talking the dimension of vector space of all n cross n matrices of real entries, okay, with trace equal 0 is n square minus n. Now is the condition we have to check. So now it is not the entire vector space of n cross n matrices. Now our matrices has condition that its trace must be 0. So what is trace? If I write my matrix Aij to be I comma j from 1 to n, then trace of A or trace of A is this A11, A22, I mean sum of all diagonal entries. And what they want is that this trace must be 0. Okay, so how it looks like? So let me write a matrix first. So any matrix A in W, so let me choose A. Let us call this vector space to be W. Then A satisfying such A is such that trace of A is 0. Then A11, A12, A13 up to A1n, A or n minus 1, A1n, and here A21, A2, A31, AN1. And how it will be then? Anyone wants to guess? N minus 1, 1, AN1. And diagonals we have, right? A33, AN minus 1, N minus 1. And here AN comma N. Here A1N. So note that here these elements from here, or these elements, let me write here A32 and so on, and these elements here AN2, AN3, these elements, they do not interfere with the condition of, yes, Sakshi already said that it won't have, but how, then what exactly will be the dimension of this? So, but what we have to work on are these elements, all these, those which are in the diagonal, right? So, and what I want, this A11 plus A22 and this up to ANN to be 0. Okay, so what I can do is, let this n minus 1 terms in the row to be anything you want. And what I will do is, this last term, ANN, I will choose this to be minus of A11, A22, up to AN minus 1, AN minus 1, N minus 1. Then trace will always keep on getting 0. Okay? Is there any doubt here? Like how this is happening? So the rest terms here, these are how many terms here then? N minus 1. These are again this one and this. So n minus 1 and so on. Plus these n minus 1 many elements. Or if we want to say that all the elements are independent, only this element here, let me change the color of this. This one is depending on the other. So this only the element which is changing the dimension or which is dependent on the other elements. So the dimension will be n square minus n, because these are n square many elements and only one I am making independent on the other. Is there any doubt here? Like how this is happening? Not this one. If we said no doubt, others like Karthikeyan and Aarti. Okay. Sakshi also doesn't have any doubt. So no doubts, right? I mean, I'm just making, what I'm doing is, I want to follow that condition that trace, I want to make it to be 0. So what I will do, there are n elements in the diagonal. I kind of vary n minus 1 elements, and the last one I make it minus of the remaining n minus 1 element. So this last element become dependent on the rest other elements. So that's why this element can be omitted from the basis. And so the basis becomes all the elements except for this last component. So it is n square minus 1 elements. Yes, it is n square minus 1. Because n square minus 1, because these are all these elements except for the last one are all contributing to the basis. This last element is only we are excluding from the basis, because this we are making dependent on these elements. Okay? Okay, it's clear to Karthikeyan. Any doubt here? Like how this is happening or why this is happening? Still anyone has doubt like why this is n square minus 1 and not n? Because we are only making this purple kind of or whatever this color, this element to be dependent on the other. Rest are contributing to my basis. Okay. So dimension is n square minus 1. So this becomes false because here they are saying the dimension is n square minus 1. So this is false. Okay. Not last, but yeah. Next example would be the dimension of vector space of all n cross n symmetric matrices. Okay, now they are asking about the symmetric matrices and they are saying that dimension will be n plus 1 by 2. And what is the guess? So symmetric matrix means that if A transpose is A. Okay, so if I write this matrix as A11, A12, A1n, A21, A. Okay, no guesses. Please guess something, whether it's true or false. And now I want this to be equal. And what condition we have, that A transpose is equal to A. It we saying that this is true, and which is correct, because if we take now this, now I'm getting transpose. So suppose this is A and A is equal to A transpose, that's what we have. So this is again A11, A21, A31 and AN1, and now it will be A12, A13, A1n, and so on, and here ANN. Okay, so what I have, so whatever in the diagonal, it remains same, right? So A11 or AII are as it is. I mean, what we are getting when we compare AII is equal to AII for all 1 less than equal to I less than equal to N. Okay, but others, what I have, AIJ is equal to AJI for all 1 less than equal to I less than equal to J less than equal to N, or I can make it strict. So the elements which are contributing to the basis, or the coordinates which are contributing to basis, are these. Everything which is above the diagonal. So here it will be, let me write 3, 3 and A3n and so on. So these are elements, and the second last row will have this AN minus 1, N minus 1 and AN minus 1 N, and this two elements here and this one. So how many elements coming from first row? N. Second row N minus 1. Third row N minus 2. And last it is 1. And second last 2. So what is this? This is addition of 1 plus 2 up to N. And what is this? N. N plus 1 by 2. And so we have N plus, and this is the same as what we have here. Okay. Any doubt? The AIJs, so once I fix something above the diagonal, below, for example, once I fix A12, A21 has to be equal to it. So I need not take this in my basis, because now this element is become dependent on this one. Is there any doubt here, like what is happening or anything, or it is clear? It is clear. Okay. If you have any doubt, please stop and ask at any time. And now the last, not the last, fourth one. Now they are asking about the dimension of vector space of all n cross n matrices. N cross n. Now they are talking about skew symmetric matrices. Skew symmetric matrices everyone knows, right? And they are again saying that skew symmetric matrices with real entries is again n plus 1 by 2. And what is your guess in this case? Will this be equal to n plus 1 by 2? Skew symmetric matrix means A transpose is equal to minus of A, or A is equal to minus A transpose. Let me write it this way. So in that case, what will happen? This A11 or A12 will be minus AII. So what this will imply? That all these terms are 0, right? Everything in the diagonal becomes 0 in this case. Is it clear? Because now, for example, if I take this A11, A12, A1n, A21, AN1, ANN, now this is equal to minus of A11, minus of A21, minus of A31, minus of AN1, minus of A12, minus of A21, minus of ANN. Any doubt here? The diagonal is becoming 0 in this case. And what about the rest elements? Once I fix A12 here, it has to be equal to minus of A21. And similarly here. So what is give me, once I have Aij, then Aji is fixed and it has to be minus of, yes, exactly. As Hetvi said, it will be n minus 1 by 2. And how it will be, I will explain you again. Once, and so this is when I is equal to j, and this is when I less than j. Okay. So the only elements which are contributing, so this is anyway the diagonal now has become 0. Diagonal has become 0, and the rest elements which are congruent, oh, these have become 0, and so here only these two elements are contributing, only one element. In the second row, one element, third row, two element, and last row it will be n minus 1 element till here. So here from first row it is 0, from second row 1, and it goes up to n minus 1 here. So it is addition of 1 plus 2 plus n minus 1, which is n minus 1 n by 2, and that's what we had suggested. It is n minus 1 by 2. So what they have asked here is false, okay? Because dimension is n minus 1 by 2. Any doubt? Like how it is? N many terms are gone here. And rest we are taking only the elements which are below the diagonal or above the diagonal. We don't care. These elements only contribute to our basis. I mean, when I'm saying contribute to the basis, I hope you understand what I'm saying, okay? Because earlier when we work on this first example, every component was giving me one element from the basis. That's why. So when I'm saying that only these elements or only the elements which are below the diagonals are contributing, it means that element, for example, the element corresponding to this basis or the basis element corresponding to this element is contributing to our new basis, for example, or this is getting complicated. When I'm saying only this is contributing, means that A12 into this 0, 0, and only the first entry here 0. This is in our basis. The yellow ones are in our basis. I mean the matrices corresponding to these coefficients are in the basis. Is there any doubt like what I'm saying or anything? Please unmute or chat, write in the chat. Like how this is happening. If it is not clear, please let me know. I will again explain. Anyone has any doubt? No. Okay, great. So we will move to this last question. It is clear to Aarti as well. Okay, so we'll move to last question. And we have to check like which of the following form the basis, not the basis, a basis of P2R. And what is P2R? It is polynomials with the degree less than equal to 2. Okay. So we want to check the following sets, whether they form basis of P2R or not. And what is your guess? Whether this is basis or not. So first of all, understand that P2R has this standard basis 1x x square, right? And what this gives me, the dimension of P2R is 3. Okay, so it is know that if dimension of some vector space is, for example, k, then any given vector basis for that vector space will have k many elements. Okay. Okay, it's true. And why? Because here we have 3 elements. So what we need to check in this case is whether these elements are linearly independent or not. Okay, so this is the only work remain. And this is because of the corollaries and the proof of replacement and the replacement theorem and its various corollaries. So here we have some set with the 3 elements, which is equal to the dimension of our vector space here. So we only need to check whether this set is linearly independent or not. And as Arti suggested that this will be linearly independent. So let us check. Take all the constant terms together plus bx plus cx square is equal to 0, and this will give me 2a plus b plus c is equal to 0, b is equal to 0, c is equal to 0, and these two will give me that 2a is equal to 0 and a is equal to 0. So this set a is linearly independent with cardinality of a or the size of a to be 3. Therefore, a is basis of P2R. Any doubt here? So once we know the dimension of vector space, we need just, and if I have a set of that cardinality, I just need to check whether it is linearly independent or not. And in this case, it is linearly independent. So this set forms the basis of P2R. Second, let us check. Now, this is quick guess. And I want everyone to answer that. And what is your guess in this case? No. So even before I finished writing, the moment I wrote the first element of first term of fourth element, everyone is saying false. And it is false, or B is not a basis of P2R because B is linearly dependent set. And why? Because cardinality of B is 4, which is greater than 3, which is our dimension of P2R. And from the corollary of replacement theorem, yes, even we said that cardinality of B is 4, which is greater than the dimension. So this B is not, I already wrote, but let me write again, is not a basis of P2R. Any doubts? No. Okay, so now the third one. We will check. One minus 2x or minus 2x square minus 2 plus 3x minus x square 1 minus x plus 6x square. Whether this is basis or not, how can we check? Can we directly say whether this is basis or not? Just looking at the cardinality. Just tell me, just by looking at the cardinality, can we guess whether this is basis or not? In this case, this particular case, when C. No, we can't check. Okay, Hetvi said that we can't directly say just by looking at the cardinality, because we have the cardinality here to be 3. So we have to check whether this gives me the linearly independent set or not. If it is linearly independent, great, then we will have the basis. If not, then this C does not form a basis for our P2R. Okay, so let us start and check whether this set is linearly independent or not. Okay, minus 2 plus 3x plus x square minus x square. And this is equal to 0. And then a minus 2b plus c. I'm taking all the constants together. And now all the variable constants, it is linearly independent. Yes, it will be linearly independent. We will check. Okay. Plus 3b minus c x plus minus 2a. This was x square. Yeah. Minus 2a minus b plus 6c x square is equal to 0. And we have these 3 equations when I compare them coefficient wise. And minus b plus 6c is equal to 0. And what is your guess? How can we solve this? Any guesses? Add equation 2 and 3. Okay. So let us do that. 1, 2, 3. So what they are doing is they are adding equation 2 and 3 and then solving it. Or we can do is from the equation first, we can directly get a is equal to 2b minus c, right? And what I can do is I can substitute this in second equation, 2b minus c plus 3b minus c is equal to 0. And this will give me what? 4b minus 2c plus 3b minus c is equal to 0. And this gives me 7b minus 3. No. 7b minus 3c is equal to 0. It's 2 or minus 2? It's minus 2. So minus 4 plus 2c. So it is minus b plus c is equal to 0. So b is equal to c. Is it clear? And now I have b is equal to c again. So now I substitute this in the third equation again. So it is minus 2, 2b minus c minus b plus 6c is equal to 0. Now b is equal to c. So minus 2, 2c minus c plus 6c is equal to 0. And this will be some number here into c is equal to 0. And this will give me c is equal to 0. And when I substitute it here, I will get B is equal to C is equal to 0. And again, when I substitute it here, 2 into 0 minus 0, I will get 0 here. Okay. So as Hetvi said, you can just add these two equations, and whatever equations you get, just simplify them. And you can also do something like this to get the linear independence or dependence or coefficients for the basis. Okay, so C is linearly independent set here. Okay, so coefficients which we got are A, B, C. They're all 0. So linearly independent with cardinality of C is equal to 3. Therefore, C is basis for P2R. Okay, any doubt? Okay, no doubts. And now the last one again. Let me write D. 1 plus 2x minus x square, my comma 4 minus 2x plus x square. What is your guess? Only two elements. Whether this is basis of P2R? Okay, Kartikeya said no. Okay, Aarti is saying true, this is basis. Aarti, that's what you are saying, that this is basis of P2R? Okay, even Hetvi is saying that this is basis of P2R. Okay. So, this is actually not basis of P2R. And why is it? Because this set has dimension or the cardinality 2. And as a replacement theorem, one of the corollaries of replacement theorem said that if dimension, or let me write this, it need not be exactly in this same language, but it, or theorem, whatever it is, that let V be a finite dimensional vector space, and if dimension of V is some n, then any basis beta of V has cardinality or size n. Okay, so what this says, that any set which has cardinality greater than n or less than n can never form the basis of vector space V. Okay, in this case our vector space V is P2R, and as we all know, the dimension of V, I mean the V is our P2R here, is 3, right? But what is cardinality of D? Cardinality of D is 2, which is less than 3. So this cannot form the basis, okay? Can somebody tell me why? Because of this theorem, yes, but can somebody explicitly give me one element which does not belong to this set? Any doubts here? Doubts? Do you understand this theorem? What this theorem says? That if B to be basis, it has to have cardinality equal to the basis. All the bases have the same cardinality. We can't have bases with different cardinalities in the case of finite dimension. Okay, so that's why this is not a basis of P2R. Any other questions? Is it clear? Which is dimension of, let me finish this. Therefore, D is not basis of P2R. So, anyone has any doubt in this case? Now, let us check this set. Fifth one. Let us take E to be this set. 1 minus x, x minus x square, 1 minus x square. What about this set? Is this basis or not? What is your guess? Can we directly say in this case it is basis or not? It is basis. That's what Hetvi is saying. How are you suggesting that this is basis? Is it because it has cardinality 3? Okay, it is linearly independent. No, it is linearly dependent. So Hetvi is saying that this is linearly independent, but Aarti is saying that it is linearly dependent. Okay, so in this case, we can't discard that this is not linearly or this is not a basis because it has cardinality 3. So we have to go by our standard method that we need to check that whether this set is linearly dependent or independent or not. So let us collect all the coefficients plus minus a plus b x plus b minus b minus cx is equal to 0. And what this is giving me, a plus c is equal to 0 minus a plus b is equal to 0 and minus b minus c is equal to 0. So what this gives me? This gives me b is equal to a, and then the last element gives me c is equal to minus a. But what this is? So if c is equal to minus a, b is equal to a, then what I have here, if I substitute this in third equation, I get minus a plus a is equal to 0 and 0 is equal to 0. Then what is your suggestion? What is your guess? This is linearly dependent, independent. What is it? What is happening to A, B's and C's here? C is equal to minus A, B is equal to A. And from this statement, what I have, B is equal to minus C. But what is minus C? Yes, so A belongs to R. So what this state, then again I can check that this becomes linearly dependent set. Even this has cardinality 3, this is linearly dependent set. I can take A in R, B equal to A and C equal to minus A. Okay. Then I can have this linear combination where I can choose, let us particularly choose A to be 1, then 1 into 1 minus X plus B will be again 1 into X minus X square, and C will be minus 1 minus X square. And this, if you see, this will give me 0. This 1 is getting cancelled with this minus X is getting cancelled with this, and this X square is getting cancelled with this. But I have linear combination equal to 0 and coefficients not all equal to 0. So understood that. So this is first time. So I mean, from all these examples, this was the example where the cardinality was 3, but the set was linearly dependent set. Okay, because this is obtained, I mean, this third element, if we see, if I give this name U, V, W, then we can observe that here U plus V is actually giving me W. Okay. So that's why this set was linearly dependent set. So even though cardinality of E is 3, but E is linearly dependent set. Therefore, E is not a basis of P2R. Any doubt? It was quick observation. I mean, even if you observe this initially, that U plus V gives me W, then that itself will give us that this is not a linearly independent set. So once we have linear dependency, it cannot be basis. So for something to be basis, we must have that it has to have cardinality equal to the dimension, and it should be linearly dependent, and it must span the entire space. Okay, so any doubts so far what we did? Any doubts in previous questions? I mean, we are anyway, it's 5 now. Any doubts in this question or in the previous question where you couldn't understand anything? Kartikeya, Aarti, Sajjad. No. Okay, so understand from this and please go through the notes which are available in the portal for the course, and read those. Keep in the mind all the theorems which are quick to remember, and also try to solve all the questions, and please try to do this exercise which I suggested here, where this T I was asking to take the has a span to be equal to V and work. Okay, and a video of this lecture, the recording will be available, and also the notes, and the lecture the video and notes for the last lecture are available in the problem solving session section in the Swayam portal. Okay, please go through it. If you have any doubt, you can always ask in the discussion forum as well. So I guess no more doubts, right? Or please ask. I hope everyone could access the previous notes and lectures for the problem solving session. Anyone there who could not access those? Okay, so I assume that you could all get those. So please feel free to ask the questions in the discussion forum, and we will meet next week, same time at 3 p.m. on Saturday. Thank you. So we are ending the session now. Thank you. Yes, thank you all.